Today's lesson is on solving systems of equations. We're going to learn how to solve systems of linear equations in two variables using graphing, substitution, and elimination. Please remember to take notes. So why are we learning this? Why even learn how to solve a system of equations? Well, a system of equations can be used to solve many real-world problems. We use them when we want to solve problems that contain more than one variable. So for example, they can be used by companies to determine what price point will produce the most profit. They are used by chemists when producing and preparing solutions. You can use them when buying a car based on gas consumption. You can use them to decide which service or utility is most cost effective for you, and many, many more. So what is a system of linear equations? Well, a system of linear equations is a collection of linear equations involving the same set of variables. So remember, by linear equations, we mean equations that have two variables, x and y, that are also the equations of lines. So these two red equations here are an example of a system of linear equations, as well as the blue. Notice to have a system of anything, you have to have more than one. And what we have more than one of is equations. So there are at least two equations here for two variables. So what does a solution look like? Well, a solution to a system of linear equations is the point where the lines intersect, because remember, we're talking about lines here. So suppose I have these two lines. Notice the point 1, 1 here where they both cross is referred to as the solution to the system of equations. It's the point that exists on both lines. So when we're solving system of equations, there are three possibilities. One is that we get exactly one solution, as we saw on the previous slide. This occurs where the lines intersect at a single point. In this case, the solution to this system is x2, y negative 2. It's also the possibility that you get infinitely many solutions. And this occurs where the two lines are really the same. So here we have this purple line directly on top of the black line. They're really the same line. So every single point along the line is a solution. So we get infinitely many solutions. And then there's the possibility that we get no solutions. That occurs when the two lines are parallel, but they have different y-intercepts. So notice these lines are never going to cross, so there's never a solution. So the infinitely many solutions case, remember that's when the lines are really the same line. We call those coincident lines. That just means they really are the same line. They're a line on top of each other. They have the same slope and the same y-intercept. So take a look at this example. Here we have y equals 3x plus 4 and 2y equals 6x plus 8. The lines look different. However, when you get them both in slope-intercept form, you notice that we really do in fact have the same line. That is because if we take the second equation and divide everything by 2, we end up with the line y is equal to 3x plus 4. So all I did was divide everything here by 2 to get the y by itself. And now we can see that this line and this line are really the same line. They're identical. So that would produce infinitely many solutions. Likewise, here's another example where we have lines that are really the same line. So there's two ways we can do this. One would be to arrange them both so that they're in slope-intercept form and then make sure that they're identical. Another one is just to simply reduce the second equation to produce the first. So notice that if I divide everything in the second equation by 3, so if I divide 6 by 3, I get 2x. If I divide 9y by 3, I get 3y. If I divide 24 by 3, I get 8. So notice now that we really have, again, the exact same equations. So that tells me that there are infinitely many solutions because they are in fact the same line. Alright, so make sure that both equations are simplified, and if they are exactly the same, then you have infinitely many solutions. What about when we have no solutions? Well, that happens when we have parallel lines that have different y-intercepts, as you saw in the graphical example on the second slide. So notice here I have an equation y equals 3x plus 4 and y equals 3x plus 5. they have the exact same slope, 3. So now I know that these lines are parallel, but they're not the exact same equation, right? This one crosses the y-axis at 4, and this one crosses the y-axis at 5. So I know here that I have parallel lines that will never touch, and that means that there's not going to be a solution. There's going to be no solutions. And again, here I have a second example of two equations, both written in standard form, where if I change them to slope-intercept form, we'll see that we indeed do have, in fact, different lines, but with the same slope. So in this case, if I really want to take 2x plus 3 equals 8, I could change that into the slope-intercept form by subtracting 2x from both sides. Then I would have that 3y is equal to negative 2x plus 8. Then I could divide everything by 3 to get the y by itself. And we end up with the equation y is equal to negative 2/3 x plus 8/3. Okay, so that's the first equation. Now I'm going to go ahead and convert the second equation here into a slope-intercept form. So 6x plus 9y is equal to 40. I'll divide both sides of this, I'll subtract 6x from both sides of this equation to isolate the term with y. And then I'll divide everything by 9 so that I'll get y is equal to negative 6 over 9x plus 40 divided by 9. And notice that negative 6 over 9 really reduces to negative 2/3. This is an x here. So these two lines have the same slope but different y-intercepts. So there are parallel lines with no solution. We're going to learn 3 different ways to solve a system of equations. We're going to learn how to do it graphing, with substitution, and finally with elimination. So when do we use them? Why do we learn 3 different methods? Well, each method is good depending on the problem that you're given. Alright, graphing is really only good when you're looking at a graph itself, and you can easily just look at it visually and say that's where the 2 lines cross, so that's the solution. That's the really only time that I would want to use graphing. Otherwise, I'd prefer to use one of the algebraic methods, which is either substitution or elimination. Substitution is used when at least one of the equations already has a variable isolated. So in one of the equations you have x equals something or y equals something. Then that's a good time when you might want to use substitution. Elimination is good when the equations are in standard form, like 3x plus 2y equals 10 and 2x minus y equals 8. So there we'd have equations in standard form, and that's when we'd want to use elimination. Elimination is also good when you're solving a system that has more than 3 variables. We won't be doing that today, but you will be doing that in the future, and you'll always want to use elimination in that case. So let's take a look at this, solving systems graphically. So suppose I'm giving this graph and I'm asked, what's the solution to the systems of these equations? Well, that's easy. You just look at where the 2 lines cross. And they cross right at that point. So the solution is 6, negative 5. Make sure that you write your solution as an ordered pair where we have the x coordinate first, right, followed by the y. Alright, now we could also say, let's answer the second part of this question, which is what system of equations is represented by this graph? So they're really just asking us here, what are the equations of the lines? Alright, so the very first question you should ask is, what is the y-intercept? So I'm going to do the blue line first. We can see that the y-intercept is 3. Right, now we need to find the slope. So to find the slope, I need to count how to get from one point to the next. And I'm looking at where they cross at a corner so that I can identify the point. So I'm going to identify a second point on this blue line. And I picked this point here that happens to be at 3, negative 1, crosses right at a corner. Now I go ahead and I'll count the slope to see what we get. So notice that we had to go down 4 and to the right 3 to get to the second point. So our slope is negative 4/3 because going down, remember, is negative on the rise, and going to the right is positive on the run, and slope is rise over run. Alright, so now we can write the equation of the line in slope-intercept form, where we know that the slope is negative 4/3, and that the y-intercept is at 3. Okay, now I'm going to write the equation for the purple line. So again, it's like, what is the y-intercept? Well, there it is. We can see it. It's right there at negative 2. Now I'm going to identify a second point on the graph. Well, we might as well just pick a point. The closest one I see that crosses at a corner is this point at 2, negative 3. So I'm going to go ahead and select it. And then now I'm going to count the slope. So to get from this point, to get from the y-intercept to the second point I chose, I have to go down 1. So that's negative 1. And then to the right 2. That's positive 2. So now I know that the slope is negative 1/2. Now we have all the information we need to write the equation of the second line. So the equation of the second line is y equals negative 1/2 x minus 2 in slope-intercept form. So now you try. Take a moment to pause the video and tell me what is the solution to this system of equations. There's the solution. Right there, the green dot. They happen to cross at 1, 0. And that's it. And this is when I'd want to use graphing the most. I'm given the picture. I'm given the two lines. I'm asked, what's the solution to this system? Well, then it's really easy to visually inspect it, see where the lines cross, and list that point. That is your solution. Otherwise, I want to use one of the other methods. So let's talk about substitution first. So what is substitution? Well, substitution means to put something in place of something else. We substitute one value or expression for another. All right, and like we stated earlier, substitution is ideal to use if one of the variables has already been isolated in the original systems of equations. So for example, take a look at this system of equations. Here we have our two equations. The second equation here is written what we call in standard form. The x's and y's are together on one side of the equation. But the first equation here has y all by itself. It's in slope-intercept form, right? So y is isolated. And this is an example of when it might be to our advantage to use substitution. Let's talk about how. So suppose I have this system of equations, 2x plus y equals 8, and y equals 2x plus 4. So my first equation here is written in standard form, but my second one, the one that I have here in purple, is written in slope-intercept form, or we have already y isolated here. It doesn't have to be y, it could be x being isolated, just as long as one of the variables in one of the equations is all by itself. So let's talk about how we use this. So since I know that y is really equal to 2x plus 4, remember these two expressions are equal. Since y is equal to 2x plus 4, then wherever I see a y in the second equation, I can replace it with that expression. So right here, I took that y was equal to 2x plus 4, the one that's y equal, and I substituted it into the other equation for y. So notice how I replaced y with what y is equal to in the second equation. So it's like I just cut it. The way I think about it is cut and paste. Like if you're in a Word document and I came over to this section here, what y was equal to, and I highlighted it and I hit cut. Then I went into the other equation and I highlighted the y here and I hit paste. So I just cut and pasted this expression for y into the other equation because that's what y is equal to. The reason that helps us is because now I have an equation that just has one variable in it. And when we have an equation that just has one variable, we can solve for that variable. Alright, so in this case, I have like terms, 2x and 2x, which added to 4x. And now I have a two-step linear equation where I can solve them using inverse operations. So in this case, I subtract 4 from both sides. And then finally I divide both sides by 4 to get 1. We're not done yet because 1 is just what the x value is. Right? When we're solving a system of equations, we need to know what the x and the y is. We're trying to find values for x and y that satisfy both equations simultaneously. Meaning whatever answer I get when I plug them into the x and the y in the first equation, I'll get a true statement. And also when I plug those same x and y coordinates into the second equation, I get a true statement. So we're half done. We're half done because I found what x is equal to in this case. Now, the easy part. Usually getting the first variable is the hard part. The second part is what we call back substitution. So now that I know that x is really equal to 1, I can go back to one of my original equations. It doesn't matter if it's the first equation here or the second one, and replace x with the value that we now know it to be, 1. I'm going to choose the second equation because y is already by itself. It seems like it would take one less step to solve for y if I plugged x into the second equation here as opposed to the first one. But you would get the same answer either way. So I'm going to choose the second equation here to substitute x back into. So I'm going to replace this x right here with its value of 1. So now that I get y is equal to 2 times 1 plus 4, so y is equal to 2 plus 4. So now we know y is equal to 6. So now that I know that x is 1 and y is 6, we write our answer as an ordered pair. Notice the order does matter. This is the x coordinate and this is the y coordinate. Let's take a moment to pause the video and see if you can use substitution to solve this system. Alright, so I'm looking at this system and I'm thinking, this is a good candidate for substitution. Why? Because in the first equation, we have one of the variables isolated. In fact, in this case, we have the y variable again isolated. So I'm going to use that to plug in what y is equal to in for y in the second equation. I'm going to replace it. We substitute it. We cut and paste. So notice when I rewrote this, all I did was replace y with 2x plus 7 because that's what y is equal to. Notice that I put parentheses around that expression if there's more than one term. That's because we don't want to multiply just 2x by 5, right? We want to multiply all of what y is by 5, which is 2x plus 7, the whole thing. So I put it in parentheses to let me know that I need to distribute that negative 5 to both terms. And that's how we got to the second step here. So I took 5 and I multiplied it by both of these terms, distributive property. And again, now I have an equation that only has one variable in it. So then we can solve that equation just using our inverse operations. I combine like terms to get 13x plus 35 is 9. I subtract 35 from both sides. So that 13x is negative 26. And then finally I can divide both sides by 13 to get the solution of x equals negative 2. Or rather, to get half of the solution, right? We got x. Now we need to get y. So I'm going to go ahead and grab that first equation again where y is already by itself. I'm going to substitute negative 2 in for x. So this is the part that I call back substitution. Once you get that, and again, it wouldn't have mattered which equation I picked to plug in the negative 2. Like I could plug it into this purple equation and solve for y, and I would get the same answer. I'm just choosing the one where the variable is already isolated because that's the quickest way to get to y. It's the less steps. So in this case, I'm going to replace x with negative 2 and simplify, and we get that y is equal to 3. So finally, we report our answer as an ordered pair. It would be written as negative 2, 3. And that's our final answer. So again, this is the substitution method, and we use it when one of the variables is already by itself, already isolated. We plug it into the other equation. There's where the word substitution comes in, because we substitute it into the other equation. And then we have a system, that we have an equation that only has one variable. We solve for that variable, and then we plug that answer back into one of our original equations to get the next variable. So now finally we're going to talk about the third way to solve systems of equations, which is by elimination. So although all three methods have their advantages in certain situations, if I had to pick just one of these methods for you to learn how to solve a system of equations, it would be this one. It would be solving them by elimination. The reason why is that many real-world word problems, a little tongue twister there, are going to be set up in standard form, like you see here in step 1, ax plus by equals c. The problems just translate easier into that description. And also, when you get into the higher grades and you start solving systems with more than 2 variables, you're going to want to use this method. The other methods become too cumbersome, and in fact, you can't do them with graphing after that. So the very first step when we're solving a system of equations by elimination is to put the equations into standard form that we discussed earlier. So to get the variables on one side of the equation this time equals a number. Then you got to determine which variable to eliminate, right? And eliminate is just another word for get rid of. So the way we do that is we look at the variables and we're looking for them to have the same but opposite coefficients. So we're looking for one of the variables to have the same but opposite coefficients, or else we have to find what we call the least common multiple for one of the variables. So that'll become more clear when we do an example. Finally, step 3, we multiply if we need to, and then we add the equations. So the idea is, the goal is that we can add 2 equations together to eliminate one of the variables. And the reason that works is because if one of the variables has opposite but equal coefficients, say like negative 3x and positive 3x, when we add those equations together, minus 3x plus 3x would be 0 x's, or the x would eliminate, giving you an equation with just y in it. And again, that will be more clear when we do the example on the next slide. And then finally, the last 2 steps are the same as what we just did for substitution. All right, so once we have one of the variables solved for, we plug that value back into one of the original equations to solve for the remaining variable. The last thing that you'll always want to do is check your solution. All right, so once you've got your answer, your ordered pair, you can substitute those values back into each of the original equations to make sure that you end up with a true statement. So all of these systems of equations are easily checked. So here's a little poll question. I want you to pause the video and think about this. What is the first step when solving with elimination? So we just recovered this on the first slide. What is the first step when we solve with elimination? That's right, we should put the equations into standard form. So let's start with this example. X plus y equals 5 and 3x minus y equals 7. Step 1. Put the equations into standard form. Well, in this case, they already are in standard form, right? We got the x and y's on one side of the equal sign in both of our equations. So we get x plus y equals 5 and 3x minus y equals 7. Okay, step 1 is done. The next thing we do is determine which variable we want to eliminate. All right, so remember what I'm trying to do when I say eliminate. I want to add the 2 equations together, and I want to add them so that when I add them, one of the letters, one of the variables goes away. And the only way that happens is when you have a positive and a negative equal and opposite coefficients in front of one of the variables. So in this case, if you look, the y's have opposite coefficients, because this y really has a coefficient of 1, and in the second equation, this y has a coefficient of negative 1. So they have equal but opposite coefficients. So that will allow me to do step 3, which is just to add the equations as they are right now together. So I line them up so that the variables line up in the columns, and I add x plus 3y, x plus 3x to get 4x. A 1y minus a y, or a plus y minus y, cancels out. They eliminate. And then I set that equal to 5 plus 7, which is 12. Now notice that we have an equation again that only has one variable in it, so we can solve this. So I divide both sides by 4, and I get that x is 3. So the hard work is getting that first variable. But once you get that first one, the next step is easy, right? Since we know that x is 3 now, we just plug that back in to one of the equations to find the other variable. And again, it doesn't matter which equation you choose, but once you do enough of these and you start getting more experience, it's to your advantage to pick out the equation that looks like it's going to be the simplest. The one that has maybe no fractions or decimals, or the coefficients are as small as possible. So in this one, it looks like the top equation to me is going to be easier to substitute into. So I go ahead and I choose the top equation to back substitute 3 into. And so I get that 3 plus y is equal to 5, and now I solve for y by subtracting 3 from both sides, and 5 minus 3, right, is 2. All right, so we know now that y is 2. So now we have both x and y, right? We have our solution of 3, 2. Remember, always list the x first, then the y. And I want to check to make sure that I didn't make an error. All right, so what I do is I'm going to plug the solution back into both of my original equations. So in this top equation here, I replace the x with 3, and I replace the y with the 2. And so we had 3 plus 2 is equal to 5. And indeed, 3 plus 2 is 5, so that one checks. Okay, it worked in the first one, but it also has to work in the second one. Right? That's what solving a system means. It has to work in both equations. So I go ahead and I replace x with 3 and y with 2 in the second equation, and then I solve. So 3 times 3 is 9, minus 2 is in fact 7. So again, this one checks, and we know that our answer worked in both equations. So now poll question. How could we eliminate a variable in this example? So look at 3x plus y equals 4 and 3x plus 4y equals 6. Remember, our goal is to add the equations so that one of the variables eliminate, cancel. So one says that we should isolate y in the first equation. Get y all by itself here. Recall that when we're solving using elimination, we don't want to do that. We want to have the equations in standard form. So if I'm trying to eliminate a variable, getting y all by itself in the first equation, subtracting 3 to that other side is a wasted step. In fact, we would just have to undo that in our next step. Number 2 says add the equations, and that is our goal. We want to add the equations so that we eliminate a variable. But what happens if I add these two equations together right now as they are? Well, 3x plus 3x would give me 6x, and 1y plus 4y would give me 5y. That would equal 10. Notice I didn't get rid of any variable when I did that. Remember, our goal is to add them together to get one of the variables to eliminate, to go away. And right now, if I just add them together, no variables eliminate. So number 2, add the equations together, is not going to accomplish eliminating one of the variables. Question 3 says I should multiply the first equation by -1 and then add the equations. Well, let's see what happens if I do that. So remember, when we multiply by -1, so I'm going to take this entire equation, I'm going to multiply it by -1. I have to multiply every term by -1, even that 4 out there. So we'd end up with -3x minus y equals -4. Okay, so I multiplied everything by negative 1. Now what happens if I add it to the second equation? You can see that if I add it to the second equation, minus 3x plus 3x would eliminate, would cancel. So that we did in fact eliminate a variable using what step 3, option 3 suggested, multiplying by negative 1. So whenever you have equations, you're looking at them and they have the same coefficient in front of them. By coefficient, I mean the number in front of the variable. When they're identical, like in this case we had 3 and 3, we can eliminate them, that variable, just by multiplying one of the equations by negative 1. So I could have also chosen to multiply the second equation by negative 1, but not the first, and then add them, and I still would have eliminated a variable. And we can check that multiplying the first equation by negative 10, as suggested by option 4 here, wouldn't have got us any closer to eliminating a variable, because it wouldn't have produced any coefficients that are equal and opposite to coefficients in the second equation. So now we know that step 3 was right. So let's do one more example. Let's solve this system using elimination. Alright, so step 1, we put the equations into standard form. Oh, they already are. Now we have to determine which variable to eliminate. So remember, I'm trying to add these equations together so that one of the variables eliminate. And if I do that right now, I would get 2x plus 3x to produce 5x. Okay, so x wouldn't go away. I could try it with the y's. If I added the two equations, I would get positive 2y minus 1y. That would leave positive 1y. Then eliminate y. Alright, so before I can eliminate one of the variables, I have to get them to have equal and opposite coefficients. And remember, the way that we do that is to multiply one or both equations by whatever number we need to, so that I achieve that, so that I get one of the variables to be equal and opposite to the variable in the other equation. So I'm going to go ahead and do that by finding the least common multiple for each variable in this case. So between 2x and 3x, the least common multiple would be 6x. I could get both of these equations to have a variable of 6x and the other one to have an equation of negative 6x by, say, choosing to multiply this top equation by 3, and then that would produce a 6x here, and then turn right around and multiply the bottom equation by negative 2, and that would produce a negative 6x on the bottom. Alright, so you can multiply the equations by different numbers, right? But when you multiply, say, this top equation by a number, you have to multiply every term by that same number. And then you are allowed to go into the second equation and multiply it by a different number. So I kind of think of it as a little game. I'm trying to play this game where what do I have to multiply so that I can get one of the variables to be equal but opposite. And I have to decide if it's easier to do that with the x's in this case or the y's. So we notice that the LCM, or the least common multiple between the y coefficients, between 2 and negative 1, is in fact 2. So which is easier to obtain, right? Which one of these would be a fewer amount of steps so that I achieve my goal of getting the equations to have equal but opposite coefficients in one of the variables? Well, in this case, it's the 2y. Because all I have to do is multiply that bottom equation by positive 2, and then this term right here would be minus 2y. And that's what I want to see, because in the top equation we have a positive 2y. So when I add those together, the y's are going to eliminate. So let's go ahead and do that. So I'm going to multiply the bottom equation by 2. Now notice that we have equal and opposite coefficients. I did nothing to the top equation. Notice I just copied it. I just wrote it down. And I rewrote the second equation after I multiplied it by 2. And I multiplied every term by 2. Right, so that's how we got 6x minus 2y equals 10. Now I can add the equations together. So 2x plus 6x is 8x. Our y's canceled. And 6 plus 10 is 16. And finally, we have an equation that has just one variable in it. So I divide both sides by 8 in this case, and we get that x is 2. And then just like with substitution, now that I know one of the variables, I can plug it back into one of our original equations and solve for, in this case, the missing variable, which is y. So it doesn't matter if I pick this top equation to do that in or the bottom equation. Again, I'm just looking for the equation that looks like to me it would be the easiest or the fewest amount of steps to do. So generally that means ones that have no decimals or fractions, or the coefficients in the equation are as small as possible. So in this case, I didn't really see a clear choice. One was better than the other, so I just chose the top one. All right, so I replace the x here with 2 because we know now that x is 2, and now I can solve for y. So 4 plus 2y is 6. Subtract 4 from both sides, so 2y is equal to 2. And then finally divide both sides by 2, so we get that y is 1. Alright, so here's our solution, our xy ordered pair 2, 1. You always want to check your solution to make sure you didn't make a mistake. So I'm going to plug the x and the y in for x and y into both of the original equations to make sure that I get a true statement. So when I do that with the top equation, I get that 2 times 2 plus 2 times 1 is equal to 6. And in fact, 4 plus 2 equals 6. So it worked in the top equation. That doesn't prove it's a solution yet, right? It also has to work in the second equation. So I replace the x and y with 2 and 1 in the second equation, and I work out that 6 minus 1 does indeed equal 5. So now I'm guaranteed that the 0.21 is the solution to this system of equations. So now let's solve this system using elimination. So in this case I have the equation y equals 7 minus 2x, and I have that 4x plus y equals 5. The first step is always to put the equations into standard form. So I notice that the top equation here, our first equation, isn't in standard form, right? It's in slope-intercept form. All right, so this might be a good candidate. If I was going to solve this system, I might use substitution. But let's go ahead and solve it with elimination. All right, so that requires first putting the top equation into standard form. So this red equation that I wrote here is the result of me adding 2x to both sides so that I can get the x and y together on the left-hand side of the equation. All right, we do that with inverse operations. So I move the negative 2x term to the left-hand side of the equation by adding 2x to both sides of the equation. And this was the result. Okay, so now I have both of these equations in standard form. The x's are lined up, the y's are lined up, the numbers are lined up. And now my goal is, what I'm thinking to myself is, okay, I want to add these together, but first I got to make sure that one of the variables has equal and opposite coefficients. So I look at my equations and I try to decide what would be easier to eliminate. Should it be the x's or the y's? Well, I don't have any that are equal or opposite right off the bat. You know, I want to see like minus 2x and a plus 2x, or a minus y and a plus y. Well, we're pretty close. Look, we both have positive 1y in both equations. All right, so since the y's have the same coefficient, all I need to do is pick one of them to multiply by negative 1. Right, because multiplying by negative 1 will change the signs on everything in one of the equations. So I went ahead and I chose the second equation to multiply by negative 1. I could have just as easily chosen the top equations. As long as one of them is minus y, I'm happy. Alright, so I go ahead and I multiply the second equation by negative 5, and there's the result. And now I can add them together. So a 2x plus a negative 4y is negative 2y. The y's canceled out. And then 7 minus 5 is 2. So I get the equation negative 2x equals 2. Now I can solve for x using inverse operations. And we get that x is equal to negative 1. We just divided both sides by negative 2. That was it. So remember, all the work is really getting that first variable. And then they tend to break down, because now that we know one of the variables, right? We can plug it into one of our original equations and get the other one, the back substitute. So I'm going to plug x back into the other equation. We know that x is -1. So I'm going to choose the top equation to plug it into. Why the top? Because it looks like it will be fewer steps because y is already isolated. Could I plug -1 into the second equation for x and solve for y? Absolutely, you bet. So I think that might be a good exercise for you guys to do. Try plugging it into a different equation or both, and just to verify that you do in fact get the same answer. So in this case, I'm going to replace x in the top equation with its value of -1 and then solve for y. So I get that y is equal to 9 in this case because -2 times -1 is +2 and 7 plus 2 is 9. So now we have our solution, -1 comma 9. Remember, first the x, then the y. And I'm going to check them in our original equations to make sure that I didn't make any mistakes, that this is in fact the solution. So in the top equation, I replaced y with 9. So remember, make sure when you do that, that you are replacing the correct variables with the correct numbers. So it's the y that's 9 here, so 9 is equal to 7 minus 2 times x, and x is -1, so -2 times -1. So now I'm checking to make sure this is true. Remember, 7 minus 2 times -1 is the same as saying 7 plus 2, which is in fact 9. And then I check it in the second equation, so I replaced x with -1 and y with 9, and then I simplified and got that -4 plus 9 is in fact 5. So this solution of -1, 9 worked or gave me true statements in both equations. So I know that it is the correct answer. So take a moment to pause the video and work out the solution to this system of equations. Alright, you should have got the answer 5, 4, that x was equal to 5 and y was equal to 4. So let's see how I'd go about solving that. Alright, so my goal is to try to add the equations together. Not just add them, but make sure that when I add them, one of the variables eliminates. So I can't do that right off the bat the way the equation is set up. They're both in standard form like I like. You know, so I have my nice little columns of x and y and the numbers. But I can't add them together right now and eliminate a variable. But what catches my eye in this problem is that I got a 3y in the top equation and a 3y in the bottom of equation, so they have the same coefficient. All right, so that lets me know that all I have to do to make one of them a -3, like I want to see, is to multiply that equation by -1. And it doesn't matter which equation I choose to do that with. I'm just going to do it to the top equation. So I'm going to say I'm going to multiply this entire top equation by -1. Right, then I have to distribute that -1 to every term. So we get that 2x minus 3y is equal to -2. Alright, so that was the result of multiplying the top equation by -1. The reason why I wanted to do that is to ensure that I had equal and opposite coefficients on the y variable. Right? As soon as that I noticed they were the same, that kind of jumped out at me. I knew I had to multiply one of the equations by -1. Didn't matter which one. Now that I've done that, I can do my first goal of adding the equations together and eliminate one of the variables. So here I have a positive 2x and a positive 1x, so they add up to 3x. The -3 and the plus 3y, they cancel, they eliminate. That's why we chose to multiply it by that -1. And then finally, -2 plus 17 is positive 15. I can divide both sides by 3 to solve for x and get that x is equal to 5. All right, so we can see that here x is in fact 5. Well, we know the answer is D already because it's the only one that has x is equal to 5, but let's go ahead and get the second variable, y. So now I'm looking at our two original equations. I'm trying to decide which one of these would be easier to solve for y. And since there's less coefficients and there's no negatives down here in the second one, I'm going to choose that one. But again, it doesn't matter which one you choose. Alright, so I'm going to choose the bottom equation to substitute x back into. So I say that 5 plus 3y is equal to 17. So notice how I just took this 5 right here, which is equal to x, and I replaced it with what x is in the second equation. Now finally I can solve for y using inverse operations. So I'd subtract 5 from both sides to get the term with the y isolated all by itself on the left hand side. And 17 minus 5 is 12. And then finally divide both sides by 3. So we'll continue solving for y, and we get that y is equal to 4. Alright, so there's our two answers. We get x is equal to 5. So I write that first in my ordered pair, and y is equal to 4. So this point, 5, 4, right, represents the solution, meaning that if I did graph these on a graphing calculator, you would see that they cross again at that point, because that's what our solution represents graphically. In this case, the solution here was D, points 5, 4. If you wanted to check that, right, you could just go back up into your original equations and replace the x with 5 and the y with 4 and check that you get true statements in both of your answers. So some of you that have done this before or have seen it before or have taken many multiple choice tests like you get on the computer when you're taking your checkpoints and your exams, also notice that if you had no idea what to do, right, you could start with the answers, because in this case it's multiple choice, so you know one of these has to be right. So you could take turns if you really wanted to, plugging 2 in for x and then 2 in for y in the top equation to check if this was the solution. And as soon as it didn't work in one, then I would go on to the next point and try it. Remember, this only works when you have a multiple choice test and you know that one of them, the answers listed, is there, right? Otherwise, if it just says here, solve this system of equations, guessing and checking is not going to work. You could guess and check forever and never hit the solution, especially if your solutions were fractions and decimals. All right. So that concludes today's lesson. If you need to review any of it, you always can go back into the video and pause it and write down the steps you need from whatever method you're trying to use. Make sure you go back into the course announcements and answer the asynchronous questions for section 5.